What is RLHF? You ask an AI a question. It gives you a confident, fluent answer. But it is wrong. Or worse, it is harmful. A model that has read the entire internet can write beautifully. But reading everything does not teach you to be helpful. It does not teach you to be honest. It does not teach you to be safe. Reinforcement learning from human feedback (RLHF) is the technique that bridges this gap. It is the reason ChatGPT feels like an assistant and not just a text predictor. It is the reason Claude declines harmful requests instead of complying. Today on Neural Monk, we go deep on RLHF. The 3 stages, the math, the failure modes, and what comes after. This is how AI learns to align with human values. Before we explain the solution, let us understand the problem. A language model is trained to predict the next token. Given a sequence of words, what word comes next? This objective, called next token prediction, produces models that are astonishingly good at generating fluent, coherent text. But fluent is not the same as helpful. Statistically likely is not the same as honest. Completing the pattern is not the same as following an instruction. A raw base model, asked how to make a bomb, might answer. Because on the internet, questions are often followed by answers. A raw base model might agree with everything you say because agreement is statistically common in conversation. A raw base model might confidently state things that are simply false. This is the alignment problem. And the 3 properties we want are what Anthropic calls the 3H framework: helpful, harmless, honest. RLHF is the engineering solution to this problem. RLHF is not a single technique. It is a 3-stage pipeline. Each stage builds on the previous one and addresses a specific limitation. Stage 1 is supervised fine-tuning, or SFT. We show the model thousands of examples of ideal behavior. Question, ideal answer. Instruction, ideal response. The model learns to follow instructions and produce structured replies. Stage 2 is training a reward model from human feedback. We generate multiple responses to the same prompt. Human labellers rank them, which response is better, and why. The reward model learns to predict these human preferences. It becomes an automated judge for response quality. Stage 3 is reinforcement learning using an algorithm called PPO. We use the reward model as a signal to further fine-tune the language model. Over thousands of update steps, the model learns to produce responses that score higher on the reward model and therefore align better with human preferences. Each stage is necessary. None of them alone is sufficient. Together, they produce an aligned AI assistant. Let us go deep on stage 1, supervised fine-tuning. The goal of SFT is simple. We want the model to learn the format and style of helpful, structured responses before we introduce any human preference signal. To do this, we create a dataset of prompt response pairs. A prompt might be, summarize this article in 3 bullet points. The paired response is written by a human expert. Here are the 3 key points. Another prompt might be, translate hello to French. The response is just, bonjour. These pairs cover a wide variety of tasks: summarization, question answering, translation, coding, creative writing, and reasoning. The model is trained on these pairs using standard cross-entropy loss. It learns to produce outputs that match the style, length, and structure of the human written examples. After SFT, the model is significantly more useful than the raw base model. It follows instructions. It stays on topic. But it still has problems. It can be sycophantic, agreeing with the user even when the user is wrong. It may still hallucinate facts. And it has no built-in safety filter. That is where stage 2 comes in. Stage 2, training the reward model from human feedback. After SFT, we have a model that follows instructions. Now we need to teach it what good looks like from a human perspective. Here is the process. For the same prompt, we generate multiple responses from the SFT model. We show these responses to human labellers and ask them to rank the responses from best to worst. Not just to say which one they prefer, but which one is more helpful, more accurate, more honest, and less harmful. These pairwise rankings are collected at massive scale. Tens of thousands, hundreds of thousands of comparisons. We then train a separate model, the reward model, to predict these rankings. The reward model takes a prompt and a response as input. It outputs a single scalar score. How good is this response? The training objective is called ranking loss. It pushes the score for the preferred response to be higher than the score for the rejected response. After training, the reward model is our automated proxy for human judgment. Instead of asking a human every time, we just ask the reward model. This is the bridge between human preference and machine learning. Stage 3, Reinforcement Learning with PPO. We now have a reward model that scores responses. The question is, how do we use that signal to improve the language model? The answer is Proximal Policy Optimization, PPO. In the language of reinforcement learning, the language model is the policy. It takes a prompt, the state, and generates a response, the action. The reward model assigns a reward to that response. PPO updates the language model weights to maximize future rewards. But there is a critical constraint. The updated model must not drift too far from the original SFT model. We enforce this using a KL divergence penalty. KL divergence measures how different the new model's distribution is from the SFT model's distribution. If the model drifts too far, the KL penalty kicks in and reduces the effective reward. Why is this constraint so important? Without it, the model might discover ways to fool the reward model. It might produce very long outputs or repetitive phrasing that scores well on the reward metric but is actually useless to humans. This is called reward hacking. The KL penalty is our safety rail against this failure mode. After thousands of PPO update steps, the model is aligned, helpful, harmless, honest. RLHF is powerful, but it has well-documented failure modes. Let us go through the 4 most critical ones. The first is reward hacking. The language model is optimized to maximize the reward score. But the reward model is an imperfect proxy for human preferences. The language model can learn to exploit gaps in the reward model, producing responses that score well but are actually low quality. For example, extremely verbose responses may score high on helpfulness metrics even when they are unhelpful in practice. The second challenge is labeller bias. Human labellers have preferences. They may prefer confident-sounding responses, even when those responses are factually incorrect. They may carry cultural or demographic biases. These biases get baked into the reward model. The third challenge is scalability. Collecting high-quality pairwise rankings from human experts is expensive and slow. At the scale needed for frontier models, this is a significant bottleneck. The fourth challenge is distribution shift. The reward model was trained on outputs from the SFT model. But PPO produces a model that generates different kinds of outputs. The reward model may not generalize well to these new outputs. These challenges are why RLHF has continued to evolve and why new methods like DPO and constitutional AI have emerged. RLHF has limitations. The field has responded with better methods. The first major advance is direct preference optimization, DPO. DPO makes a clever mathematical observation. The optimal RLHF policy has a closed-form solution in terms of the preference data. You do not need to train a reward model at all. You can directly optimize the language model on the preference pairs using a single supervised learning step. The training objective is a log ratio between the probability of the chosen response and the probability of the rejected response. DPO eliminates the need for the reward model and the RL training loop. It is numerically more stable. It is significantly cheaper to run. and the results are nearly identical in quality to full RLHF. The second advance is constitutional AI from Anthropic, the technique behind Claude. Instead of relying on human labellers to rank responses, constitutional AI uses a set of written principles, a constitution. The model reads these principles and uses them to critique and revise its own outputs. An AI model then acts as the judge, replacing the human labeller entirely. This approach is called RLHF, reinforcement learning from AI feedback. It scales much more efficiently than human labeling. Together, DPO and CAI represent the next generation of alignment techniques. RLHF is not a research curiosity. It is the backbone of every major AI product today. Let us look at how the leading AI systems use it. ChatGPT and GPT-4 from OpenAI were the models that brought RLHF to the world's attention. GPT 3.5 was fine-tuned using RLHF with a team of about 40 labellers. GPT-4 used a much larger labeling effort and more sophisticated reward modeling. Claude from Anthropic uses constitutional AI, a variant of RLHF that replaces human labellers with an AI model guided by written principles. This makes Claude's alignment more scalable and more principled. Gemini from Google uses a hybrid of RLHF and RLHF techniques developed by DeepMind. Llama 3 from Meta, which is open source, uses a combination of RLHF and DPO for its alignment, making advanced alignment techniques available to the research community. Mistral and Mixtral use DPO primarily, demonstrating that the field has moved beyond the original three-stage RLHF pipeline. GitHub Copilot uses code-specific RLHF to align code generation with developer preferences. The pattern is consistent across all of them. A base model, combined with human or AI preference data, produces a system that millions of people trust and use every day. Let us bring it all together. RLHF, reinforcement learning from human feedback, is the technique that transforms a raw text predictor into a helpful, honest, and safe AI assistant. The alignment problem: base models predict tokens, not human intent. The 3H framework: helpful, harmless, honest, these are the targets. Stage 1, SFT, train on expert prompt response pairs to learn instruction format. Stage 2, reward model, train on human pairwise rankings to learn preferences. Stage 3, PPO, use RL to maximize reward scores, bounded by KL divergence. The key failure mode is reward hacking, mitigated by KL penalties and iterative RM refresh. DPO eliminates the reward model entirely, directly optimizing on preference pairs. Constitutional AI uses written principles and AI feedback, scaling alignment without humans. Every major AI assistant you use today, GPT-4, Claude, Gemini, Llama, Copilot, is shaped by RLHF or a direct descendant of it. RLHF is the reason AI went from generating plausible text to being genuinely useful. If this video helped you understand RLHF, the next one in our All About LLM series covers RAG, Retrieval Augmented Generation, how to ground AI in your own data. Subscribe to Neural Monk. See you in the next video.